tell you about that in a minute. And then in the second half, I'm going to talk about some recent work, which is work in progress, so it's a little bit more informal, perhaps. So this is work I've done with Andy Elvidge at UEA. He's at the Met office as well. And the previous work was also done with Ian Brooks at Leeds and colleagues at British Antarctic Survey, John King, Alex Weiss, and Tom Lappin Cope. So I realized I took their names off, so I just thought I'd mention that. So what I'm going to be, the overall theme then is thinking about how the atmosphere and sea ice interact and the exchange of momentum between those two interfaces. And the recent work is looking at the atmospheric response to marginal-ice-zone drag parameterization. So, you know, at the risk of telling you things you already know, we need to parameterize the way that the atmosphere and sea ice interact, and this is usually done by the definition of a drag coefficient here, which has got, as written here, it's got three components. There's a skin drag over water, there's a skin drag over ice, and then there's a form drag. So if you look at the sketch here, the skin drag is in red, and the form drag is essentially the atmosphere hitting vertical surfaces and imparting momentum in that way. What we've done in this study here is take a well-known, or perhaps not that well-known, but a state-of-the-art parameterization for the form drag component developed by Christoph Lütkers in Germany, where he basically uses mathematical modeling to come up with expressions for how to parameterize the momentum exchanged by the atmosphere hitting these bluff surfaces. Okay, so I'm not going to go through the details here because that's not the purpose of this particular talk, but suffice to say that you can parameterize this form drag component by essentially the roughness length and various observable coefficients which relate to the things like the flow sizes, the roughness at the edges, and so on. And there's some tunable coefficients in there, of course. We all like a tunable coefficient. So there's things like the effective resistance and other things. As I say, I'm not going to go through that, but sheltering function, flow length, and so on. What you can take away from this is that each of these three things, the skin drag components and then the form drag, all can be parameterized in the most simple way, but as a function of ice area or ice fraction. So as I said in black here, we can parameterize using the ice concentration. And if you're running a weather or climate model, then that's good news, because this is something that is fairly easy to pull out of that, and we don't need to worry about all these subgrid scale quantities which we can't easily observe. So there's still some tuning to be done within this parameterization, and a few years ago we had a field campaign up in the Arctic where we flew 2 different aircraft in areas of the marginal-ice-zone as part of this ACCACIA field campaign. And one of the aims of this field campaign was to try and measure the drag coefficient and the ice fraction, and therefore get some numbers that we could put into this parameterization. So we had two different aircraft, as you can see there, and we flew around 8 flights in areas. These are all the low-level legs. This is sea ice here, and on one particular, I think, mean over the period, and this is the maximum and minimum extents of the marginal-ice-zone during, this was March 2013, March and April 2013. So, quick primer on how you would calculate the drag coefficient from aircraft data. Well, basically, you need to have some fairly adventurous pilots who are happy to fly in the atmospheric surface layer, so typically around 30 to 40 meters above the sea surface. You use your aircraft to measure wind perturbations, so the three-dimensional wind field, you subtract the run mean, and then you get wind perturbations, and you can calculate the surface stress from those wind perturbations. From that, you can calculate the friction velocity U star, and you can use Monod-Nabokov similarity theory to calculate a roughness length based on the wind profile, stability corrections, and the roughness and the friction velocity. And then you can use this to essentially calculate a neutral drag coefficient based on the roughness length, the aerodynamic roughness length. Okay. We also needed to measure the ice concentration, as I said earlier. So we had two ways of doing this from the aircraft. We had measurements of albedo, which we got from shortwave radiation measurements, and we could also measure surface temperature from an infrared thermometer from the aircraft, and we used some statistical processing to try and get the best relationship we could there, which I'm not going to go into just now. But essentially, we ended up with a collection of around 200 data points. So this was more than double the number of data points available previously from all previous studies for the marginal-ice-zone. And so each data point represents an average of ice concentration and drag coefficient for a run length of about 8 kilometers. Okay, so we divided up our flights into legs and then runs of about 8 kilometers. And that distance was chosen based on a statistical analysis of what would give you the best representation of the turbulence in the atmosphere. So it's dictated by atmospheric turbulence, essentially. Okay, so here's some results. So this is from one flight with the large aircraft. The background field is austere sea ice concentration, and the blue dots here are ice fraction from the aircraft. And you can see that the aircraft is broadly matching the austere, so going from open water to over the sea ice, you're getting ice fractions of less than 20% up to 100%. And when we plot the exchange coefficient for momentum, the drag coefficient, you can see we've got relatively low values, around 1 or less than 1, up to moderately high values, more like 3 to 4, or even over 4 times 10 to the minus 3 in the middle of the marginal-ice-zone. And then as we get up into areas of higher ice concentration, 100% ice concentration, it looks like the drag coefficient starts to go down again. Just to give you an illustration, we were there with the aircraft, of course, so we were able to look out the window and use video and photographic analysis to sort of look at the morphology of the sea ice. So, for example, for this area here, where we've got quite a high drag coefficient, you can see the sea ice looked like this, smallish to medium-sized pancakes with quite ridged edges, and it looks quite rough visibly, and it proves to be quite rough aerodynamically. So that's just one flight. As I say, we had around 200 data points over about 8 flights, and what we've done here is we've binned the drag coefficient into ice concentration bins from 0 up to 1. The numbers in the black, so the black squares are giving you the median for each bin, and the numbers are the number of data points within each bin. And the left panel is using ice fraction based on the albedo, and the right panel is ice fraction based on the sea surface temperature. And to be honest, I just concentrate on one of these. They qualitatively show the same sort of thing, but obviously there's a slight difference in methodology as to how we calculated the ice fraction. So what can you see? Well, there's that result that we saw on the previous illustration here, where you go smooth conditions, rough conditions in the marginal-ice-zone, and then to smooth conditions again. That seems to be broadly represented when you look at all the data compiled together. So we've got relatively low drag coefficients here over the open water, increasing to a maximum value around ice fractions of 0.6 and 0.8, and then decreasing again to a value of just over 1 for the solid sea ice conditions. One of the aims of all this was to try and calibrate this parameterization that Christoph Lütke's and his group developed. So we've got 2 different fits to the Lütke's parameterization here, one in black and one in grey. The black one has these coefficients, and the grey one these ones coefficients. And you can see that we can get a pretty good fit of this parameterization scheme by tuning these effective resistance coefficients in the sea ice Morphology coefficients, so these are both, as I say, sort of slightly tunable parameters. We've tuned them within the range of what is reasonable. But the take-home message is that this parameterization scheme, tuned with our observations, seems to do a pretty good job, and we're able to get it to go through the medians or close to the medians in most of these sea ice fraction bins. So that's all good news. We also broke our data set into two parts, so north of Svalbard in Fram Strait area, south of Svalbard in the Barents Sea area. So this is south of Svalbard and Barents Sea, about half the data points in this area. This was quite a mobile area, lots of small scale pancake type ice. It looked like this a lot. And when we fixed our endpoint to this value here, which was quite a rough value, and our open water point to here, without any tuning, we can get a pretty reasonable fit, certainly through the interquartile ranges for the parameterization scheme in this area. When we go to the area in Fram Strait, so north, the sea ice tend to be much smoother up here. It was less broken up, less marginal-ice-zone, more sort of big flows, kilometer scale flows. Again, around half the data points were in this area. And again, if we fixed the 100% value using our observed 100% value, and then we could get a pretty good fit of the parameterization scheme going through the medians in very well there. So here I'm summarizing at the time of when we published this paper back in the beginning of 2016, end of 2015, these were the parameterization schemes that seem to be in common use in a selection of weather, climate, and sea ice models. So the black and the grey lines are observational fits based on the Lütke's parameterization, and the coloured lines are from the various models here. So you can see that the SICE-5 model, it was had a similar form drag parameterization added by Michel Sandos the previous year, and it does a pretty good job of fitting our observations. And the ECMWF cycle 41 also has this peak in exchange coefficient in the marginal ice zone, and that was introduced in 2015 or 2016, I think, partly informed by our work and Michel's work. Some of the other well-known modelling centres don't seem to account for this peak in drag in the marginal ice zone. So, for example, if you look at CCSM, the time of writing anyway, they just linearly interpolate from one value over the sea ice and whatever you have over the ocean based on the Charnock relation and so on. And similarly for LIM 3. The Met Office model has one value for the marginal ice zone, but it's still rather low in this setting here. 4 minutes. Okay, so the new work in 4 minutes. What we've been doing more recently has been running an atmosphere-ocean model with this new parameterization included. So the Met Office model has got this parameterization as part of the standard setup now, and we've run case study simulations at high resolution for this same ACCACIA period here. And we've done 3 experiments. We've done one with the new parameterization. This is the drag coefficient in black here. One with the parameterization which is smooth, which is based on what the roughness length set to in HADGEM 3, and one where it's rough, which is the current operational drag coefficient and what's been used in GSI 6 and GA 6 as well. And we've run a bunch of case studies for this period, and I've gone through this briefly. The take-home message is when you've got, so what I'm showing here is observations from the aircraft of air temperature against model data. And you can see that the model does a pretty good job of capturing the air temperature, but that there is a bias here, and this bias is around 2.1 Kelvin. When you change that to the new sea ice drag scheme, your bias drops down to 0.02. So that's remarkable, isn't it? And we didn't fiddle this, honest. So much improvement in terms of the atmospheric representation of near-surface air temperature. If you use the smooth scheme, then you get a bias of minus 0.46 Kelvin. If you look at the wind speed, you can see the wind speed is pretty noisy. You're flying through turbulent atmospheric boundary layer. Here are observations, model data. You can see that there's a correlation, but there is quite a large amount of scatter. If you look at the biases, the bias for the rough setting is minus 0.5. The bias for the new scheme is minus 0.06. So again, quite a significant reduction in wind speed bias. And we've done a second set of experiments as well using a global configuration of the Met Office model. So this is a global, a larger grid size, 17 kilometers. We've done both, and it's a global simulation using a standard Met Office test suite, which is like a collection of days spaced through the seasons. And what I'm showing here is the difference between the new sea ice drag scheme and the rough scheme, and this is the surface stress. So you can see that the new sea ice drag scheme has a much lower surface drag, as you would expect, especially in the marginal-ice-zone areas, and that leads to quite a considerable cooling reduction in near-surface air temperature. So this bias that we saw in our case studies for the ACCACIA data is important over the whole globe on the order of, a similar amount, 2 or 3 Kelvin. So conclusions then, we'd argue based on our recent observational analysis that CDN is now reasonably well constrained. We've got 200 data points, more than doubled what was previously available. We'd recommend that parameterization schemes in sea ice and climate models should have a peak in the marginal-ice-zone, and that the Lütke's parameterization does a pretty good job, especially if it's tuned with some minor changes based on our work. And we've got some, and you can read more about that in this ACP paper here. We're doing some ongoing work which is trying to quantify the impact of this on the atmosphere. Initial work suggests we find significant improvements in wind speed and air temperature biases. So thanks for your attention.
Some questions?
Say, what was the origin of the cooling, and isn't there a separate heat transfer coefficient that we could tune as well?
So the transfer of scalars is dependent on both the roughness length and the roughness length for the scalar. So the cooling is a result of the decrease in the roughness length, not where you have left the scalar roughness length the same in these experiments. So one of the things we tried to do with our observational data was quantify the relationship between the scalar exchange coefficients. The difficulty was that the atmosphere was quite close to neutral conditions in a lot of the flights, which means your errors mean that the exchange coefficient for heat and moisture has very large errors associated with that. So despite a lot of work, we weren't really able to say anything meaningful about that. So, ongoing work.
Quick question? Yes, thank you very much.